So how do we use Coriolis to describe the major flows of surface air around the globe, the so-called prevailing winds? Well, let's consider where the descending arms of the Ferrel and Hadley cells meet at that 30 degrees plus or minus latitude. Let's just think about the southern hemisphere because it's mirrored in the northern hemisphere. So in the southern hemisphere, at that 30-degree mark, we've got the subtropical ridge, exerting that high pressure. Surface winds at that high pressure diverge, and because of Coriolis, the deflection is to the left, which means that below, or latitudes higher than 30 degrees, you get prevailing westerlies. The westerly winds, they form under the Ferrel cell, and they flow west to east. And you may have heard of the roaring 40s as one of the major winds that sailors delight in and driving them across vast expanses of ocean very quickly. Above the 30-degree south and towards the equator, we have the trade winds, the easterly trade winds. They form under the Hadley cell, and they're always seen as the reliable, steady winds that sailors can use to get around, and that's good. Just remember, though, that at the equator, there's that very expansive area of low pressure as a result of that intense heating, the intertropical convergence zone. That low pressure system being so expansive, pressure gradient force across the intertropical convergence zone is weak. So what you end up getting some light winds and often no winds, and it's what the sailors of old would have referred to as the doldrums in the tropical area. Coriolis is also very weak there, but we'll come back to that later. What have I missed out? We got the polar easterlies and the like. But basically, it's the deflection of the winds from that diverging airflows to the right in the northern hemisphere and to the left in the southern hemisphere as a result of Coriolis that define these major prevailing winds. And when we look at these things in real life, so here we have a sequence of daily imagery acquired by the 4 geostationary satellites, that is permanently fixed over the same position of the Earth, covering the whole globe. We see these winds in effect. So the westerlies between 30 and 60 degrees in latitude, very fast moving. You can see them flicking across the bottom here, long bands of cloud moving from west to east. Between 30 degrees and the tropics, you have the easterlies, the east moving flow of air. You can sort of see these cyclones forming over Australia and then moving to the east, to the west, so the easterlies, the trade winds. So let's think a bit more in detail about the Coriolis force. So if we put a parcel of air in a pressure gradient field, the parcel will move from an area of high pressure to low pressure. That's the pressure gradient force at work. But if we're in the southern hemisphere, there'll be a deflection of the motion to the left. What happens when pressure gradient force and Coriolis force balance? You get a flow that is parallel to isobars. Now, isobars are the contour lines, recall, of the pressure system. And where in the past we had the depiction of air flowing out perpendicular to the at right angles to the circle as a result of air going from high to low. In this case, is deflected to the left or counterclockwise out of the high pressure system as a result of Coriolis force. Into a low pressure system now, where we would have otherwise had the air just going straight down into the low pressure cell, we have the deflection as a result of Coriolis, but it is clockwise into a low pressure system. So counterclockwise out of a high, clockwise into a low. And so let's talk about this equalization of pressure between Coriolis and pressure gradient. So here we have a parcel of air starting off in a region of high pressure. So as it starts to equalize, it starts its journey towards equalization, it moves through pressure gradient force. But because we're in a rotating sphere, in this case is a southern hemisphere depiction, the actual motion is deflected to the left because of Coriolis. So the resultant forces, if you know about resolving vector fields, is Coriolis is deflecting to the right, which is actually to the left in the motion, to direct left of the direction of motion. The next time slice, that pressure gradient force is becoming stronger, contribution to the actual motion, until eventually it balances the pressure gradient force and the actual motion is parallel to the isobars. When pressure gradient forces and Coriolis forces are in balance, when they equalize each other, you have what's called geostrophic flow. Geostrophic flow is is flow of air parallel to isobars. But because there's surface friction, what we don't see is, we don't see columns of air just spinning endlessly around a pressure cell. We see an eventual equalization, but it persists for a while. So here we have an example. Here's a high pressure system that airflow out of the high towards the low, but because of the deflection of Coriolis, it wants to be isotropic, but because of surface friction, it sort of weakens the strength, and what ends up happening is equalization, coming counterclockwise out of the high, clockwise into the low. So you start to see these sort of flows as a result of that pressure gradient force and Coriolis force trying to equalize, but frictional force comes to play here. You eventually get the equalization of those two cells rather than the geostrophic flow. As I said, you get that anti-clockwise or counterclockwise flow out of the high, clockwise into the low. And when we try to remember that, you can play the game of cyclone and hurricane, or hurricane. Cyclones are a low pressure system, so too are hurricanes. But how those columns of air spiral into the low pressure system, which is at the eye of the cyclone or eye of the hurricane, how the direction of flow, in this case counterclockwise, this case clockwise, determines whether you're looking at a cyclone, is clockwise circling into the low, or counterclockwise circling into, in this case, a hurricane.